So we're looking at the homework on alternate forms of the derivative, and we're going to look at some differentiability stuff, so let's just jump in here. All right, so the directions are explain what each limit statement represents, and then evaluate the limit. Do the work on a separate sheet of paper. Well, I'm not going to do that. I'm going to do it right here. So in number one, I'm looking at a form of the derivative, and part of the way that I know that is I see a difference quotient, so I have y number 2 minus y number 1, and then the h is like the delta x, and that's x number 2 minus x number 1. I see a limit statement, so I have to be careful to look for all of these things. Now the next thing that I notice is that right here I have the variable of x, so it's a variable, and I have a variable of x here. So that leads me to believe that I'm looking at the general form of a derivative. So the next question, once I figure out that I'm looking at a derivative and I have a general form, I want to answer the question of what? Derivative of what? This is not an at what because it's not point specific. All right, so the next thing I need to figure out is what function am I finding the derivative of, and I can clearly see that I'm using sine of x plus h and the sine of x. So my statement here would be, what does this expression represent? It represents the general derivative of sine x. I'm not going to write that out, but you can check your work. The general derivative of sine x. So that's the first piece of information that I was supposed to figure out, that this expression represents the derivative of sine x. And the second thing it says is to evaluate the limit. So without doing any algebraic workout, now that I know that I'm finding the derivative of sine x, I know that the derivative of sine x is cosine x, and so that is the evaluation of that expression. Moving on to number 2, again I can see a y number 2 minus a y number 1, and we know that delta x is x2 minus x1. Now this time, instead of having a variable here and a variable here, I have a specific, and that's really important, I have a specific value. So that's finding the derivative at c. So this is a point-specific derivative. That's the next thing I want to figure out. All right, so now that I notice it's a point-specific derivative, I want to answer two questions. The derivative of what and the derivative at what? Well, the of what, the function that I'm identifying here, I can see that I'm using the cosine function and the cosine function, so I'm finding the derivative of cosine x. And the at what is pi over 3. So when I explain the limit statement, I would say the expression represents the derivative of cosine x at pi over 3. All right, now I'm going to evaluate the limit. So I know that the derivative of cosine x, the derivative, let's do d dx of cosine x, is equal to negative, don't forget that negative, sine x. And then I'm to evaluate that at pi over 3. So I have the opposite of sine at pi over 3. We know that pi over 3 is a 60-degree angle. Sine is the y value, and the sine of 60 degrees is root 3 over 2. And I'm taking the opposite of that, so I get negative root 3, or opposite of root 3 over 2 is the evaluation of the limit. So we're not doing any algebraic or trigonometric work. We're just figuring out what the expression represents, and we're going straight to the answer. In number 3, this one's a little bit trickier. This is a little different format. So here, to me, it looks like we're looking at a function minus a function at a particular value. You may be wondering what says plus here, but remember, minus a negative makes a plus. All right, so I have f of x minus f of c, because I have a specific number, over x minus c, and over here I have x approaching the c value that I've identified to be 6. So this expression represents the derivative of the opposite of x squared, so this is what I would write for what the expression represents, the derivative of negative x squared at x equal to 6. So it is a point-specific derivative. So I'm going to take the derivative of negative x squared. So if f of x is equal to negative x squared, then f prime of x is equal to negative 2x, and then I'm going to evaluate that. So this is the calculus format of asking the same question. Negative 2 times 6, which gives me negative 12. So that entire expression simply evaluates or simplifies to be a negative 12. That will be the slope of the tangent line of negative x squared at 6. Let's go on to number 4 and see what we've got going on there. In number 4, it looks like we have an f of c plus h minus f of c. So these numbers in here, like the 2 and the fact that I have a 1 right here, leads me to believe that we're looking at a c value, so I'm thinking point specific derivative. And then the next question, remember, I have to answer for myself is, if it's point specific, it's the derivative of what, and it's the derivative at what. So in this case, the of what is in that first part. The function is found where it says f of c plus h, so the function is 5 minus 3, and I'm going to take out the 1 plus h and put the x back into its place. So I'm finding the derivative of 5 minus 3x at x, or the c value at, we can say at x equal to 2. Well, since I know that my function is linear, I see right back here my function is linear, I really don't have to do much work. I know that the slope of that line is going to be negative 3, and in this case the value of x is irrelevant because my function is linear, so that's going to simplify to be a negative 3. In number 5, I see a number and I see a number, so if this is a derivative statement, it's going to be point specific. So it looks like an f of c plus h minus f of c, and don't let that plus throw you. Remember, we talked about the minus and negative. Let's see, and since my denominator has just an h in it, my c value is equal to 0. And we can check that out by going over here to the function. We are claiming that the function is negative. Actually, we're claiming that the function is negative x. Wait a minute. That's right. All right, so let's back up a little bit. The c value is not 0. The c value is, as we already pointed out back here, the c value is 2, because we can see that right there. So the function, when we take this stuff out of the parentheses and we put the x back in, the function in this case is equal to x cubed, and we're going to evaluate at x equal to, I think that was a negative 2. I covered it up. Let me uncover that. Yep. At x equal to negative 2. And so when I write this up, I would say this expression represents the point-specific derivative of x cubed at x equal to negative 2. So when I take the derivative of f of x, I get 3x squared by the power rule. And when I substitute negative 2 and I square negative 2, I get 4 times 3 is 12. So this expression simplifies to be 12, meaning that the derivative of x cubed at negative 2 is 12. So it's an alternate form of the derivative. And then the last one on this page, I have a variable and a variable, so I have an f of x minus, since I have a number back here, it looks like an f of c over x minus c as x approaches c. So it's the alternate form of the derivative. So they want me to find the derivative of f of x, or the derivative of 2x to the 1/2. I'm going to do a rewrite on that. I'm going to use the power rule to find the derivative. So half of 2 is 1, decrease the power by 1, 1/2 minus 1 is negative 1/2. And I'm going to evaluate that at the c value, which is 9. So f prime of 9 is equal to I have a negative power, so I'm going to take that to the denominator and rewrite that as the square root of 9. So that's going to give me 1/3, so that expression simplifies to be a 1/3. All right, let's go on to the next page. In the next page, I have another general derivative because I see a variable, and I see variables. So the function in this case is found in the here I can find it either in the front section by taking out the x plus h and putting x back in, or I can see clearly that the function is negative 4x cubed plus 7x. So this is the general derivative of negative 4x cubed plus 7x. I'm not going to have a specific c value. And so when I find the derivative using the power rule, I get negative 12x squared plus 7. And that's what that expression simplifies to be. In number 8, looks like a point-specific derivative. As in this case, n approaches, it looks like the c value is negative pi over 2. Looks like the function, so here's f of x minus f of c, over x minus c. So my function is sine, in this case n, they're using the variable of n instead of x. The derivative of sine n or sine x is cosine of n, and we're going to evaluate that at pi over 2, and we know that the cosine of pi over 2 is 0, so that expression simplifies to be 0. The explanation here would be the point-specific derivative of sine n at n equal to pi over 2. All right, let's go to part B. In part B, we're determining whether the statements are true or false, and if the statement is false, we're going to explain why or give a counterexample. In letter A, it says, the slope of the tangent line, so the derivative, of or to the differentiable function. So they're telling me that this mysterious function has a derivative everywhere. So that's the point of telling me that I have a differentiable function. So the derivative does exist. At the point 2f of 2 is, so over here I see a difference quotient. I see a y2 minus a y1 over, and x can represent x, or h can represent x2 minus x1. What I do not see is a limit statement. So I cannot be expressing the derivative in calculus format if I don't have a limit statement. So this will be false. And the explanation would be there is no limit. So this is not a derivative. It looks like it wants to be a derivative, but it's actually just a difference quotient. So it's not a derivative, not instant rate of change. All right, so let's clear that, clear the annotations. In part B, if a function is continuous at a point, then it has to have a derivative. Now we know our classic example that we've looked at when we looked at differentiability is our absolute value function. So if we look at the vertex down here, the absolute value function is continuous. However, the absolute value function at the vertex is not differentiable. Therefore, continuity does not guarantee differentiability. Whoops, I didn't mean to do that. Let me grab my pen again. So, where was that? Continuity does not, continuity does not guarantee differentiability. All right, so that's important. Letter C, if a function has derivatives from both the right and the left at a point, then it is differentiable at the point. Well, nice, over here we have our classic, like we already said, our absolute value function, and all the values on the left side have a derivative. If it's just the basic y equal absolute value of x, all the slopes over here are -1 and all the slopes over here are +1. So there are derivatives from the right and left, but they're not in agreement. They're not moving me towards a derivative at the vertex. So if a function has a derivative from both the right and the left, then the function is differentiable. That would be a false statement. Oops, false. Come on, you can do it. And then finally, if a function is differentiable, has a derivative at a point, then the function is continuous. That is true, because remember, if a function is not continuous, then there's no derivative. So if the function does have a derivative, then the function has to be continuous. So differentiability implies continuity. Differentiability implies continuity. So if a function has a derivative, the function is continuous at that value, but not the other way around. And finally, in letter C, this question should actually state, use calculus to explain why the function is differentiable at the given value. Now, the way that we're going to determine that, because we have a piecewise function, is we're going to determine the left derivative, and we're going to look at the right derivative. And when I say the left derivative and the right derivative, I mean coming from the left and coming from the right. So the left derivative would be governed by this piece according to the piecewise, because remember, that's to the left of 2. So when I find the derivative on the left side, f prime of x, if I find the derivative of x squared plus 1, I get 2x, and I'm going to evaluate that at x equal to 2. So f prime of 2 is 2 times 2, which is 4. So the left derivative is moving me towards 4, and then the right derivative would be this piece over here, 4x minus 3. So the f of x for this piece is 4x minus 3. The derivative is 4. And if we evaluate that at x equal to 2, of course, and it doesn't matter what we're evaluating it at, we get the derivative to be 4, so f prime of 2 is 4. So we have left derivative agreeing with right derivative, so this function is differentiable at x equal to 2. So whenever you find the derivative of a piecewise function, you find the derivative in pieces. You find the derivative of the first piece and check it, and you find the derivative of the second piece and check it.